Okay, sorry about that. Disaster struck last video, so a couple problems. I meant to pause the video and accidentally stopped the video. And then when I went back just to skim and see what the video looked like, I realized that I wasn't screen sharing for the entire second half. So I'm going to redo everything that I was talking about at the end of last video such that you can actually see it in Excel. So what I meant to show you is that I have the input data already. I've got values for the van der Waals constants A and B. I've got a temperature, noting that it is degrees Fahrenheit plus 460. That'll give me degrees Rankine. And then I looked up the value of the gas constant for the appropriate units. So the first thing I want to do is plot P versus V under bar. And that will give me a sense for what the data should look like. I'm sorry, plot the reverse. I want to plot V under bar is on the x-axis, P is on the y-axis. So I'm going to start with a couple values of V under bar, and I know that my B value is 1.6, so I want to start something a little bit above that. And I learned this last time that if you go small steps, you'll get a better, smoother looking curve. And I'll plot a lot of data. I want to calculate my P now. So this is the van der Waals equation of state. It is R times T, R times T divided by V under bar minus B minus A divided by V under bar square. Okay, that looks good. So that makes sense. At very low molar volumes, my pressure should be extremely high, and it should drop very quickly. So I want to plot all this data now. So I'm going to highlight it all and insert a smooth line graph. Okay, that looks good. The only thing that is wrong with it is I have to adjust my axis so that I get a better sense of the data. So I don't want to go to minus 2000. 0 is good enough just to get a good glimpse. I'll go to minus 20, and let's say I want to go to, what do I want to go to, 200 maybe? Nope, a little bit more. Let's go to 300. A little bit more than that. That's a little bit too zoomed in, 500. And minus 200. Let's keep zooming out. It's a very iterative process. Sometimes, yeah, you know what, that's fine. That's going to show me what I want to see. So it's illustrating that, again, for a couple values of pressure, excuse the poor formatting on the plot. This is just for informational purposes, so I'm not going to make it pretty. I showed you what this looks like in the OneNote, right? So this is what a cubic equation of state would look like. The problem is, for any pressures that are between about 200, let's say, and whatever the limit as this goes to infinity are, there's going to be 3 solutions for molar volume. So I want to figure out which one it corresponds to the liquid and the vapor. The middle solution, so the solution that is on this part of the curve, will never be a physically relevant solution because it's between the point where I have saturated vapor and liquid. Let's see if I can draw on this. I don't think I can. I'm on my laptop now. All right, what's next? I need to solve for V under bar given a value of P. So I want to find the saturation pressure. That is going to involve calculating the fugacity at various values of P. So the procedure here is going to be guess and check a P, and then from that P, I will calculate the molar volume of the liquid, molar volume of the vapor, plug it into that equation that I solved, or that I showed you in the last video, which I'll pause and clip. This is the equation that I want to solve. So again, I want to guess a value of P, calculate what the values of V for the liquid and V for the vapor are, plug them into this equation such that the only thing left to solve for is the fugacity. And then after that, I want to goal seek for the value of pressure that gives my fugacities equaling in the liquid and vapor phases. Okay, so let us go on a separate part of the plot now. Yeah, I want to go on a separate part of the plot. I want to guess a couple values of P. I want to guess a lot of values of P. So I have to figure out what I want to guess. I want to guess something that I'm reasonably confident is going to give me the right answer. I want to guess below that, right? I don't want to guess above the correct answer because I'm going to guess a range. I'm going to go from about 30 psi to 200 psi. And I'm going to do that in increments of 5 psi every time. I'm going to do this until I get to 200. And why did I choose these bounds? If I look at the plot, this is how doing the plot helps me. Because I see that at 200 psi, that's where I get to the maximum of this plot. I know the correct answer is not going to be above that, certainly. The saturation pressure has to be somewhere between the maximum of this curve and whatever the limit as this curve goes to infinity is. So now I need to calculate the V underbar. And for this, I need both the V underbar of the liquid and V underbar of the vapor. So I'm going to solver for this. I need to guess an initial value for V underbar. Right, so at a pressure of 30, what approximately is my volume going to be? And if I look and see if I can find a value of 30, so let's see, it goes from 209 to minus 299 between 2.2 and 2.3. So I'm going to guess 2.2 for all of these VLs. And I'm going to solver for this in a second. Over here, I'm going to calculate for my V underbar of my vapor. And my guess for V underbar of the vapor is going to be, let's pick 20 because that's right in the middle. Remember, the closer you are to your initial guess, the better solver will be. And then I am going to say this column is P calculated. Hold on, let me think about what I want to do here. Okay, I think I know what I want to do. Sorry for that, I'm doing this cold, so you're seeing me go through the problem solving process just like I would normally. So I'm going to try and explain everything I'm doing. So this column I'm going to call solver for V sub L. Right, and in this column I'm going to solve the van der Waals equation of state such that it's equal to 0. So I'm going to put everything on the left-hand side. So I'm going to want, in this column, I want it to equal 0, so it's going to be P minus, let's see, RT, so R $ times T divided by V of the liquid, because that's the one I want to solve for here, minus B. Minus A divided by V underbar for the liquid square. Okay, yeah, this should not give me 0 at this point, but I want to copy this all the way down. Okay, now at this point, I'm going to use solver. All right, I wanted to double check and make sure that this worked first. I noticed a quick mistake. So in my solver for V of the liquid, I forgot this minus. It was a minus of a minus, so this should be a plus. So I made a mistake there. And I already did the solver, but I wanted to show you how solver should work. So if you click on solver, it only lets you set one objective for a solver. So what I do is I set an objective for this cell L9 to be a value of 0 by changing the cells, and these are the J column is all my VLs. Oh, that just changed it. I don't want it to change it, so I'm going to highlight everything back again. And then every other equation that I want to solve, I add that as a constraint. So L10 to L42 is also equal to 0, and that will solve. And as I had predicted, all of the V sub L's are close to this 2.2. Now again, how important is that initial first step? If I had put that the V of the liquid was 200, and I guessed something like that, and now I do the solver with the same thing. So one of the benefits of solver is that it saves your last thing that you made it solve. So I could just click solve again and it'll do the same thing. But if I do this again, now I'm getting different V sub L's. These are actually the V sub V. Right? This is what the curve should look like on this side. So I'm actually going to do that in a second. So I want to undo everything I just did. Oh, maybe it's too difficult. I'm just going to, let's see. No, I want to keep things organized. I'm going to put my initial guess back to 2. And I'm going to solver everything again. Okay, that's back how I had it. Now I need another column that says solver for V sub V. And in this cell, I want to copy the formula from here, but I need to make sure that I'm getting the right values, and the only value I need to change is the p-value. All right, okay, so it should be like so. Now, if I click Solver, and I set my objective of cell M9 being equal to 0, still change, nope, I want to change the variable cells in column K now. Subject to the constraints, I need to change this that all of these cells are now equal to 0. So that's going from M10 to M42. And okay, solve. I should get back what I had just a second ago. Okay, so now I have solutions for V sub L and V sub V. Next thing to do is to plug them into this equation and solve for fugacity. So I'm going to do it in a couple of different steps. I think when you try and do too large of formulas, you get a little confused. I'm also going to try and clean this up a little bit. I like to make sure that my formatting is nice so I can easily see things, because all these significant figures bother me. Very weird about my significant figure usage. I don't want that many significant figures, so I'm going to reduce it a little so I can get a better sense for the magnitude. Oh no, I don't want to do that. Yeah, 2 significant figures is fine. All right, first thing I want to do is solve for Z, the compressibility. And that is also going to be for 2 different states, Z of the liquid and Z of the vapor. For Z of the liquid, I want to take R times T. Oops. R times T divided by P times V of the liquid. And both of those things are changing. Copy that all the way down by double clicking. And I should see that, what did I do wrong here? RT divided by PV. No, it's PV minus PV over RT. Yep, that is my mistake. So I realized I made a mistake there because I double checked in my own head. I'm trying to make sure because I know, oh, that still didn't work. As P decreases, oh, P is still 30 PSI. My compressibility should be going to 1. PV. Oh, for a gas. This is for liquid. I messed myself up. But that is, I did have it wrong before. It is PV divided by RT. So P times V divided by R times T. Did I have a parentheses? Is that my mistake? Maybe need a parentheses. Yeah, no, 0.96 is what I was expecting. Yep, I need to parentheses this. Okay, that's better. There we go. All right, so Z should be 1 for ideal conditions, which is low pressure for the vapor. Now that I have Z, let's see, what else do I need in this equation? That's it. That's all I need. So now I can calculate the fugacities of both phases. So I'm going to try and do this in one shot. I don't want to have too many columns because then things get hard to keep track of as well. So this column is going to be fugacity of the liquid phase. This column will be fugacity of the vapor phase. So solving this, remember phi is fugacity over pressure. So it is going to be P times the exponent, and in Excel that is exp is the function call. So it's Z minus 1 minus ln of Z. This is all for the liquid, remember, I'm doing the liquid phase, so I'm picking the liquid numbers, plus ln of V for the liquid divided by V minus B. And close out all the parentheses correctly. I have too many? Let's see, let's have Excel just fix it for me. Okay. I think that looks okay. Let's see, fugacity I know should be going towards pressure as pressure goes low. All right, let me double check. Oh, and I made another mistake. I forgot a completely separate term. I forgot the A over VRT term. So I need A $ divided by, not going to forget my parentheses this time. Excel is very nerve-wracking to do when you're on camera. I'm doing my best. Times R $ times T. $. Now I got to close out all the parentheses. Oh, no, I made a mistake there. The ln has to be closed out. I really like how Excel color codes these parentheses for you. It helps you make sure, double checking. Let's see, where's my red parentheses? Do I need it? I should need it. Oh, yep, you know what? I need one more there. Okay. If you guess is still a little bit higher than I want it to be. Let's double check, see what the liquid is. So just click drag over. And I need to adjust some things. So P. Okay, perfect, that makes sense, right? So my fugacity of my vapor phase should be approaching my pressure as my pressure goes lower and lower. So 30 PSI, not a super low pressure, but it's lowish. About 2 atmospheres and change, so it makes sense that my fugacity is about the same. Copy these formulas all the way down. All right, this video is getting pretty dense, so let's wrap it up by finding a solution. Remember, my solution is where the fugacity is equal, so I'm going to make it easy on me to find by saying equals 1 minus the other, and all the way down, and we'll see where that happens. Let's see, at a pressure of about 105, I'm pretty close. So I know my pressure in PSI A of about 105 is about roughly the correct answer. And at this point, if you wanted some more accuracy, what you could do is, let's see, I could zoom in here and I could guess 106, 107, 108, and so forth. But every time I do this, I'm going to have to goal seek and do solver to find via the liquid and via the vapor. So if I want some more precision in this answer, it's going to be a little bit more tricky. What you could also do is you could also just interpolate from this point. So you could treat this as your table of thermodynamic data. And you could say, if I want to find the data point where, so if I move all these down by 1, so let's say I've got or no, this is what I want to solve for, right? I want to solve and find where this is 0. I could just linearly interpolate, and that would give me where my dog wants to play with me. Where the correct answer is. So how could you do that in Excel? You would say you set the slopes equal, right? So, okay, had to think for a second. So my interpolation formula is y1 plus y2 minus y1 times, let's see, this thing is in parentheses, x minus x1 divided by x2 minus x1. And my final answer should be close to 105, closer to 105 than 110, definitely. And that will also double check that I did it correctly. 105.1, that's pretty good. So that's about the correct answer. If you were to keep doing this, the correct answer would be at 105.2 PSI absolute. So this technique does get us pretty close to the correct answer. So just to recap, how do we use fugacity practically? Well, we use it as the equilibrium criteria. So we have the equation for an equation of state. If I give you what the temperature is, you can plot an isotherm. So that isotherm is pressure plotted against V underbar, and that's where you get this signature shape curve. The problem with the equation of state is that it doesn't tell me where saturation occurs. So this line, blue line that I'm showing, is actually not the actual data that is experienced by the thing that is in vapor-liquid equilibrium. So in real life, it would stop at 105.2 because that's what we just calculated. And all this stuff, so everything that I'm highlighting, let me see if I could highlight it in a different color. So everything here, yeah, any pressure that is below 105.2. Oh, I can't highlight it. Anyway, all these data points are not actually relevant. This is all superfluous curve fitting stuff. If I want to find the actual vapor pressure of the component, that is going to be the component at which the vapor curve stops and the liquid curve begins. In order to do that, I had to solve for the fugacity of both phases, set them equal to each other. And that's what all this was in Excel. I wanted to find the point at which the fugacities were equal to each other. That tells me when I have phase equilibrium. All right, sorry for that long video. That was way longer than I expected it to be. We'll have one more video for today.